Okay, guys, the absolute last gas law. This is called the ideal gas law. The formula and the information that you need, other than what's in the problem, is on the back of your reference sheet, and I'll point out where that is. But this is about universal gases. So we say, in terms of kinetic theory, how the particles move around, that gases have to behave a certain way, right? So an ideal gas follows three criteria, and it's based on the kinetic theory, that they all have collisions, they all move in opposite crazy directions, and that they never stop. Like, it's some simple, basic, these are ideal gases. They all behave the same way. So this law involves every aspect of a gas. What is that gas's pressure? What is the gas's volume? How many moles of that gas exist? It basically means how much do you have. What's the gas's temperature? And it also involves something called a universal gas constant. Now, this is a number that some guy with absolutely no life came up with a ton of years ago that explains universally, if a gas has this specific pressure, then this number makes the math work out, right? I'm not a math guru, so I can't explain that. I just tell you how the formula works and what to do with it. So the universal gas constant is based on that number. It's a number, and it's based on the pressure unit, okay? And it's basically just to make the math work out so that you can figure out any one of these things given the other four. Notice there's 5 things in this formula: pressure, volume, the number of moles. This R stands for your universal gas constant, and then T for your temperature. So if you're given 4 of these things, then you can find any one of them, okay? So obviously the P is for pressure. It's either going to be measured in ATM, which is atmospheric pressure, or something called KPA, which stands for kilo, K for kilo, pascals. All right, Pascal is a guy who came up with this and studied gases. So Pascal is his unit for pressure, kilopascals, right? Your volume must be in liters for the math to work out. So if you are given a volume in milliliters, you must change that volume over to liters. And there's the conversion for that, which is also on your reference page. Okay? It's just moving the decimal, right? Move the decimal. N stands for the number of moles. However, I promise you, on your end of course, they are not going to give you moles. They are going to give you grams and expect you to change grams over to moles before you start working the problem. Your temperature must be in Kelvin. Remember, to get to Kelvin from Celsius, you have to add 273. I promise you, on your end of course, they're going to give you the temperature in Celsius to see if you remember. Change it over to Kelvin, right? The struggle is real. Chemistry is hard, right? And then R comes from your universal gas constant. And it is on your reference sheet. I'm going to highlight it. Right here under the word constants. And it tells you the universal gas constant R. If your pressure, right, it's based on the pressure unit. If your pressure is given to you in ATM, this is the gas constant you use. This is the R value. It's just a plug and chug. This is the number you're going to plug in your formula. If your pressure is given to you in kilopascals, then this is the R value you're going to use. Typically, this is the one you'll see. But it's on the back of this sheet. You don't have to memorize it. So you just know that when you're working this problem, to fill in R, look at your pressure unit. ATM use this. KPA use this. Right? So let's work a problem. There's a problem in your book that I'm going to work through with you. Okay? So you can pause the video and you can write down that problem. I don't have enough room on the sheet to write it down, so you can write that down. It's on page 393 in your section review. So, the problem reads, how many moles of helium gas would it take to fill a balloon with a volume of 1,000 cubic centimeters when the temperature is 32 degrees Notice it's in Celsius. And the atmospheric pressure is 752 millimeters of mercury. Okay, so this is one, how you figure out that you're dealing with ideal gas law, not Boyle's, not Charles. First of all, they mention moles. Anytime they mention moles or grams, it's probably going to be ideal. Notice there's not two of any of these. In a Boyle's law problem, you're going to be given 2 volumes or 2 pressures. Here there's only 1 of each. In a Charles law, you're either going to be given 2 volumes or 2 temperatures. Notice here, you're only given 1 of each. Okay? So they're trying to throw you for a loop here. Let me explain. They're trying to throw you for a loop here by giving you millimeters of mercury. I very seriously doubt your EOC would give you one of these, but just in case, if you look at the back of your reference sheet, right here, okay, right there where I've green marked, there are some unit conversions, and it tells you there that 1 ATM equals 760 millimeters of mercury. Now, what does this millimeters of mercury even mean? It's another pressure unit that's measured by using what's called a barometer. So if you Google barometer, it's a funky looking pan with an upside down thermometer in it. And so basically it measures atmospheric pressure or pressure in a room or any situation, because the pressure of the air will force liquid that's in that pan up the thermometer. So obviously mercury is what's inside thermometers. It's inside the barometer, inside that pan. So any pressure that exists in the room will force liquid, right? It just puts pressure on that liquid and forces it up the thermometer, right? It's called a barometer. But it's measured in millimeters of mercury because it's like a thermometer, right? It's got mercury in it. And it's measured in millimeters. So they're just trying to throw you off. But they give you this conversion on the back of your reference sheet to show you that if you're given a different unit besides ATM or kilopascals, you can convert that. So let's say we'll convert that really quick. 72 millimeters of mercury, and I need to get that in ATM, right? Whatever unit I'm given here must go on the bottom, so they cancel. And then I just plug in my numbers. For every 1 ATM, that equals 760. So I'm going to divide that out of my calculator, right? Anytime I'm multiplying by 1 over something, I'm actually dividing. So let's work that out. 72 divided by 760 means that my pressure in ATM, I'm going to do that math again just to be sure. 72 divided by 760. 0.095. 0.095 ATM. Right? So I've got my pressure unit in ATM. There's something wrong with my temperature unit. It's in Celsius. I need to add 273 to get into the Kelvin. So what would that be? 305 Kelvin. So now I've got my temperature unit set. My volume is in centimeters cubed. Like they're really, really, really trying to make this difficult. So let's look at your volume. On your sheet, you have a little, I circled it on your reference sheet. You have a little section right here that says 1 liter equals 1,000 milliliters, which equals 1,000 cubic centimeters. So 1,000 cubic centimeters is equivalent to 1 liter. You need your volume to be in liters. So now we have correct numbers. Now we have the right volume unit, the right temperature unit, the right pressure unit. We get our R from our reference page based on our pressure unit, which is ATM, and we're trying to solve for moles. Okay? So let's plug and chug. Here's your formula. We're going to plug in everything that we have in the correct spot. So our pressure is 0.095 ATM. Our volume is 1 liter. We're solving for N, which is number of moles. My R, I'm going to go to my little handy dandy reference sheet and I'm going to look up the R to use when ATM is my pressure unit. So the R to use is 0.0821. 0.0821. And now my temperature is 305 Kelvin. Wow, so now I have math on both sides, right? I'm trying to get N by himself. So the first thing I need to do, order of operations says, take care of any multiplying that you can before you start doing some major algebra. So order of operations tells me I can multiply these two numbers and I can multiply these two numbers and then I can solve for N. So let's do that. I'm multiplying 0.095 by 1, which means the answer on the right is going to be 0.095 equals N. And then now I can multiply these together. So let's do 305 times 0.0821. I'm a double checker. 25. Okay. In terms of decimal numbers, I would not worry about putting a bunch of decimals. I would, if it's close, 25.0, then I would just put 25. If it's 25.5, you might could do that. But your answers are going to be multiple choice. So you're going to see if you're close or not. If you're totally off, then that means you've done something wrong in the formula or you've missed a conversion up here on a unit. So you can just basically put a whole number. Here, this was a decimal number. So it's what it gave me, so I had to use it. So now I got to get N by himself. So I'm going to divide by 25 to get N by himself. Divide by 25. And now I get that there are 0.0038 moles of helium. That's the answer I got. Right when you're dividing, this number goes in the top on your calculator. This is on the top, he goes in first. So this number divided by 25. Yep, that's what I got. Moles of helium. Now if you want to check yourself, right, then you could put this number in place of moles and work that math out, and they should equal each other on both sides. Okay? And that's the ideal gas law.